Welcome, everyone. For today's prep, we're going to introduce our next major topic, and that is exponential and log functions. And today, we're just going to start with exponential functions. And before we get there, just want to look at what type of function really have we been looking at so far in this course. So almost all the functions we've looked at have been power functions. Well, we're going to be introducing a new type of function here called exponential. But first, let's start with power functions. What's going on with the power function? Let's look at those a little more closely. So when we have a power function, there's almost like there's two different levels to this function. There's the ground level, kind of the main part, and then there's the upstairs portion, the exponent. And with a power function, what happens is the ground level. This is our variable. So when we're talking about power functions like this, the ground level we call the base. So for a power function, the base term here is our variable. Now the upstairs portion, the exponent, in this case, when we're talking about a power function, is a constant. So our exponent, when we're talking about a power function, is just a number. It's just a constant. So with this new type of function we're going to be looking at, exponential functions, what we're going to do is we're going to kind of switch these around. So we're going to move the variable up into the exponent, and we're going to have a constant as our base term. And that's what we're going to call an exponential function. So an exponential function, we'll call the base term b, and this is just some constant. And our variable or our exponent term is going to be a variable. And this is why we call it an exponential function, because, well, the exponent is a variable. So this is a different type of function. And we're going to look at some different examples of it. And the one special case that we're going to be considering is the natural exponential function, e raised to the power x. So we're gonna investigate this number e a little bit, and we'll talk about these derivatives because those are going to be important. But first, let's just look at a couple examples of what different exponential functions look like. So let me get out of the way here for a second. And we've got a graph here with a few different exponential functions graphed out. So let's go through and I'll mention what each of these functions is. So the first one here, the lowest one, this is the exponential function 1.2, the number 1.2 raised to the power x. The next one, this is the graph of 2 raised to the power x. And then the last one, that's the exponential function 3 raised to the power x. And then the special one that's in the middle, in between 2 and 3, this is going to be our exponential function, natural exponential function e raised to the power x. Guess I'll pop up over here. So what's so special about, well, first of all these exponential functions, they all have roughly the same shape. So some of them are a little bit steeper than others. 3 raised to the x is going to be a little steeper than e raised to the x, which is going to be a little steeper than 2 raised to the x. But they all have the same general shape. And they also all go through the same point. So this point is 0, 1. So they all go through that exact same point. And What's special, one of the things that's special about this natural exponential function, e raised to the power x, is that if we were to figure out the slope of our curve at that point, well, the slope is going to be exactly equal to 1. So out of all the exponential functions, this is the only exponential function that has that property. If we were to graph the tangent line at x equals 0, only e to the x has a tangent line with slope equal to 1 at that point. So 3 to the x, the tangent line is going to be a little steeper. 2 to the x, the tangent line is going to be not as steep. And it's this property, the fact that e to the x has a slope equal to 1, that's what makes its derivative so nice. And that's why we primarily use this exponential function in calculus courses. So let's look at the derivative of e raised to the x. And it's really nice. So the derivative of e raised to the x is just e raised to the x. So really easy to remember. It's almost like you do nothing. But if you blink, we are actually differentiating the function e to the x, but not much happens. It's its own derivative. So that's a very unique property for this exponential function. Now for other exponential functions, so if it's generally just b raised to the x, well, you can kind of see you end up with the exponential function, but then you have this kind of this correcting factor, natural log b. And we'll be talking about natural log later on. So we're primarily going to be working with just derivatives of e to the x. So one interpretation of e is it's the special number that gives us a slope of 1 at x equals 0 for an exponential function. It also gives us a nice simplified derivative. But e is just, it's a fancy number, but it's just a number. So e is approximately 2.71. Now it is a decimal, so it keeps on going, and it's not a rational number, so it doesn't repeat or it doesn't stop or anything like that. And it makes sense that this decimal is 2.71. If you look at these exponentials, the graph of 3 to the x versus e to the x versus 2 to the x, it's kind of in the middle there. So even though we give it a special name, e, it's really just a number. So think of e kind of on the same way as you think of the number pi, which is 3.14. Or approximately 3.14. It's just a special number, shows up enough where we just give it its own special name. So we're calling this number e. All right. So this derivative of an exponential function, super nice. Now one little warning here. You're going to be tempted. The derivative of e to the x, you're going to be tempted to want to try and use power rule. So power rule doesn't work here. This is a different type of function. We can't use power rule for it. It's actually easier than doing power rule. But just to be careful, we're not differentiating this using power rule. So we don't bring down the exponent. We don't put it in front. We don't subtract 1 from the exponent. That's not how this works. So this is a different type of function. That's not, power rule doesn't work here. So it's got its own special rule, but it's actually a little bit easier. You don't have to really do anything. So let's try a couple examples. And we'll look at some properties. But I just want to get a little practice working with the derivative here. So we've got a function f of x, 5 minus 6x squared times e to the x. And let's try differentiating this. So what do we have? Well, if we look at this, there's a product going on. So we've got this 5 minus 6x squared term, and then multiplying that is this e to the x term. So what do we have? We've got a product. product, there's x terms here, there's x terms here, and then there's multiplication in the middle. So we got to use our product rule. All right, so good review of our product rule here. So we're going to differentiate this. So we'll call our function's called f, so we'll call our derivative f prime. And how do we do our product rule? Well, write down 2 copies of the product. So 5 minus 6x squared times e to the x. And then we'll leave a little space, write down a second copy, 5 minus 6x squared times e to the x. In the first copy, we apply the derivative to the first part of our product, and then in the second copy, we apply the derivative to the second part of our product, and then we put a plus sign in the middle for product rule. And now we've got to differentiate just the 5 minus 6x squared, and then we've got to differentiate just the e to the x. All right, so let's do that. So for the 5 minus 6x squared, derivative of 5 is just going to be 0, so that's going to be gone. We can do our regular power rule on the x squared term. So notice the difference. X squared versus e to the x. The variable there for x squared is on the base. When we're looking at e to the x, the variable's upstairs. So these are different derivatives that we're going to do. So if we do our power rule, we're going to bring the 2 down, multiply it with the negative 6. So we'll get negative 12. And then we subtract 1 in the exponent, so just negative 12x. The stuff in the middle here we're done with, so we've just rewrite it. And finally we get to this e to the x term that we got to differentiate. Well, it's nice, really nice. Derivative of e to the x, just e to the x. So you blink and you miss it. We did something. We did the derivative there. So there we have it. And that's our derivative. And one nice thing about exponentials is you can actually factor here. So this term has an e to the x in it. This term has an e to the x in it. So we can actually, if we wanted to say simplify this, we could. So directions don't say to simplify, but we know it's normally a good thing to do. So if we factor out e to the x, what are we going to have left? Well, from the first portion, we're going to have the negative 12x. And then from the second portion, we're going to have this plus 5 minus 6x squared. And, we could rearrange the terms just to give them in increasing, decreasing order for the powers of x, but that's fine. So this part's not really necessary. We could have just stopped here. All right, so we'll practice a little bit more of this in class, and also look at some properties for these exponential functions. But just wanted to see a little bit for how to differentiate these things. So we'll see you then. Bye-bye.